Hello, everybody. Welcome to another lesson on how to identify a terminating or repeating decimal expansion. In this section, we will learn how to determine if a fraction is terminating or repeating. Now, what is the meaning of terminating decimal and repeating decimal? So, what's the difference? All right, let's get into it. A terminating decimal is a decimal that has an end digit. For example, express 3 over 8 as a decimal. Now we're going to use long division method. 3 goes inside and 8 is outside here. So let us break this down. 3 is too small, so we add 0 and a decimal point. So we now say 30 divided by 8 is 3. 3 times 8 is 24. 30 minus 24 is 6. So 6 is too small, so we decide to bring 0 down. 6 divided by 8 is 7. 7 times 8 is 56. 60 minus 56 is 4. 4 is too small, so we add another 0 and bring it down here. 40 divided by 8 is 5. 5 times 8 is 40. 40 minus 40 is 0. So this is where it ends. This is the end digit. This is a terminating decimal. Let's look at another example. All right. Express 3 over 4 as a decimal. Let's see if this is a terminating decimal. So the dividend goes in and the divisor goes outside. So we'll say 3 is too small, so we add a 0 to it and a decimal. So we say 30 divided by 4 is 7. 7 times 4 is 28. 30 minus 28 is 2. 2 is too small, so we bring the 0 down. 20 divided by 4 is 5. 5 times 4 is 20. 20 minus 20 is 0. So this is our final answer, 0.75. And our terminating decimal ends at 0. So this is the meaning of terminating decimal. The end digit is always 0. There's always an ending. However, there are other situations. A repeating decimal is also known as a recurring decimal. It is a never-ending decimal whose decimal part repeats with a pattern. Now, convert 1 over 6 to a decimal. So, the dividend goes in and the divisor is outside. 1 is too small, so we add 0 and a decimal. So we say 10 divided by 6 is 1. 1 times 6 is 6. 10 minus 6 is 4. 4 is too small comparing to 6, so we add another 0 down. 40 divided by 6 is 6. 6 times 6 is 36. 40 minus 36 is 4. 4 is too small again. We add another 0 and bring it down. 40 divided by 6 is 6. 6 times 6 is 36. And here we go again. We keep having 4 as remaining. We can keep dividing. There is no ending. So what do? We just put some dots there to signify 6 is to infinity. So this is an example of repeating decimal. So we can always write it as 0.16 and put a dot on top. This tells us that it's 6 is a repeating number, is an occurring number. That's the pattern there. There is no ending. Let's try another example here. 5 over 6 converted to decimal using long division. So 5 goes inside, 6 stays outside. 5 is too small, so we add the decimal and the 0. So we'll say 50 divided by 6 is 8. 8 times 6 is 48. So we subtract and get 2. 2 is too small comparing to 6, so we put the 0 down. 20 divided by 6 is 3. 3 times 6 is 18. 20 minus 18, 2. There's a pattern here, right? So we bring it down and we keep dividing. So you see, 2 keeps repeating, and our final answer, we decide to take is 0.833. Don't forget to put the dots as to signify that 3 is a repeating decimal there. However, we could write it as 0.83, put a dot on top of 3 to tell you that 3 keeps repeating. This is an example of repeating decimal. I will show you another video on how to convert fractions to repeating decimal to decimal and repeating decimal to fractions. However, we need to identify how to identify fractions if they are repeating or terminating decimal expansion. So how do you identify a recurring decimal? It's either like this, 0.5552 to infinity, which is unrealistic because our pen can't keep writing 5 forever. So we just technically write 3 dots to identify 5 is to infinity, or we put a dot on top of 5 to tell you that 5 is recurring, or a bar too. These are the ways we can identify recurring decimals. So this is an example of a one-digit pattern. Let us consider the rational number p over q, where p, our denominator, is not 0. So if we can write the denominator in terms of 2 and 5, then the rational number p over q will be in forms of as shown below. So p over 2 powered n times 5 powered n. This is the formula used to identify a terminating or recurring decimal expansion. Now let's take a look at it. So what does this mean? If the fraction is similar or to satisfy the formula given, then the rational number will have a terminating decimal expansion. For example, let's take a look at this. 3 over 2 squared times 5 to the power of 0. Does it look similar? Yes, it looks similar. M is 2, N is 0. So this is similar. Now, let us simplify this. What does this mean? It means 3 over 4 times 1. That answer is 3 over 4. So this is an example of a terminating decimal expansion if this fraction is converted to decimal. Let's look at another example. 2 over 2 power 0 times 5 squared. So we'll say 2 over what? What is 2 power 0? 1 times 25. So that is 2 over 25. This is an example of a terminating decimal expansion if it is expanded. Now, let's take a look at recurring decimal. How do they look like? So don't forget to use this formula when necessary, okay? Now, the otherwise situation. The rational number will have a non-terminating and recurring decimal expansion. For example, this. Does this look similar to the formula given? No. 3 powered 1 is nowhere similar to the formula given. So if we simplify, it will look like this. 7 over 3 times 25, which is 7 over 25. Now, this is definitely not a terminating decimal. It's a recurring decimal. So it doesn't follow our formula. Okay, now let's do some example. Example 1, 7 over 16. Remember our formula, p over 2m times 5n. So let us expand 7 over 16. Can it look like this formula here? Now, p is 7, q is 16. Okay, so we're going to start we're going to start and work with the cube. So 16, let us break it down. So we have 2 to the 4th power, which is basically 16. As for the 5, we could say times 5 power 0, which is equivalent to 1. So yes, this could work. So our new answer is 7 over 2 power 4 times 5 power 0. Yes, this is a terminating decimal expansion. 7 over 16 is a terminating decimal expansion. That means if it's expanded into decimal form, it will terminate. Alright, now next, 13 over 150. Let's use our formula. So remember, what is P? P is 13. What is Q? 115. So let us make Q in terms of 2 powered m times 5 powered n. So we'll say 150 equals to 2 powered 2 times 3 times 5 squared. So these are the factors to get 150. So we have 2 times 3 times 5 squared. And our numerator is 13. Now, is this a terminating decimal? No. Why? Because 3 is not part of our formula. So, no. Since the given fraction, 13 over 150, is not in the form of P over 2 powered m times 5 powered n, it has non-terminating and recurring decimal expansion. So this is a non-terminating decimal expansion. So if you convert it to a decimal, it will not terminate. It will keep repeating or recurring and recurring. Alright, let's try this. Negative 11 over 75. Let's use our formula. Don't worry, negative also applies to this formula too. So P is negative 11, which we're not really going to be focused on it. We're going to be focused on the Q. So let us focus. Let's make 75 in terms of 2 powered m times 5 powered n. So let's see the factors. 3 times 5 squared. There is no 2 here. So this is it. Does it look like our formula? No, because 3 is not similar to 2m. Nope, it's not. So therefore, since the given fraction, negative 11 over 75, is not in the form of P over 2 powered m times 5 powered n, it has non-terminating and recurring decimal expansion. So negative 11 over 75 is a repeating decimal. Let's try this too. 17 over 200. Yes, this is our formula. So P is 17 and Q is 200. Let's use it in terms of 2 powered m times 5 powered n. So we'll say, what are the factors of 200? We have 2 cubed, okay, times 5 squared. All right, now this is good work. So our answer is now 17 over 2 cubed times 5 squared. Does this look like our formula? Yes, it does look like our formula. So since the given fraction 17 over 200 is in the form of P over 2 powered m times 5 powered n, it has terminating decimal expansion. So this is a terminating decimal expansion, 17 over 200. So next lesson will be radicals. Please don't forget to subscribe for more lessons. So see you soon. Bye. Ciao.